Welcome to our fourth screencast on the photoelectric effect. And what I'd like to talk about on this particular occasion is the origin of the electron volt. And hopefully you'll be able to understand where the electron volts come from and why it's such a useful way of measuring energy, particularly for very, very small objects such as atoms and things that are smaller than atoms. Okay. So, in order to help you understand this, I am going to use an analogy. I'm going to relate the idea of electric fields with something you're familiar with, which is a gravitational field. So, over here on the left, we've got a gravitational field. And here is the ground. And there's someone standing on the ground. Now, we would hopefully remember that G is the symbol for the strength of the gravitational field, and that's normally measured in newtons per kilogram. So that's the gravitational field strength. Now, over here on the right, we've got an electric field, and the electric field is created whenever we set up a separation of charge. So at the top here we've got positive charges, and down here we've got negative charges, and so that represents a separation of charge. And in order to achieve the separation of charge, we've got as a result of separating the charge, we have a voltage. So there will be a voltage between those two plates. And also, those two plates are separated by a distance, which we're going to call d. So that distance between that plate there and that plate there is d. And so, if we want to talk about the strength of this electric field, then the strength of this electric field depends on two things. It depends on the size of the voltage, and the larger the voltage, the stronger the electric field. But it also depends on the distance between these plates. And if we make this distance bigger, then the field becomes weaker. The closer these plates are together, the stronger the field. And so the strength of our electric field is equal to the voltage between the plates, in this case, divided by the distance. And if we worked out the units for the electric field strength, it would be volts per meter. Excuse me. So, we've defined, or we've familiarized ourselves with the strength of a gravitational field and an electric field. So these are the two fields. The second thing we now have to consider is what moves in each of these fields. Well, we would know from our experiences that what gravity acts on is anything with mass, okay, measured in kilograms. What does an electric field act on? Well, electric field doesn't act on mass, it acts on charge. So if we've got something in there with let's make it a positive charge, then the electric field will act on this charge in a similar way to a gravitational field acts on this mass. And in both cases, we're going to get a force. So if we look over here at our gravitational situation, then we know that the force due to the gravitational field, which is a force due to gravity, otherwise called weight, is simply equal to the mass of the object multiplied by the strength of the gravitational field. So it's the mass of the object times the strength of the gravitational field, which is m times g. Over here, on the right-hand side, we have a charge in an electric field, and it's going to also experience a force. And remember, the positive charge is going to be repelled from the positive plate and attracted to the negative plate down here. So this force is going to act in this direction. And in this case, the electric force, or the force due to the electric field, is going to equal not the mass, but it's the charge. It'll be the, I didn't write that in actually, so that'll be the charge. By the way, the symbol for charge is going to be lowercase q. And of course that was m there. So the force on the charge is going to be q, q times the strength of the electric field, which is E. So there's a similarity or a symmetry you hopefully might see there. Electric fields act on charge, gravitational fields act on mass, and in both cases a force is being applied to the particle in question. Okay, now let's have a look at both of these situations from an energy and work point of view. So let's say now we've got our mass, we're over here now in the gravitational world, we've got our mass, and we want to lift it up to a certain height. Oops, went too far. So we want to lift it up that height, from there to there. Well, we know that if we take our mass and we lift it without accelerating, just lifting it up to this height, it will have potential energy. It will have gravitational potential energy, and its gravitational potential energy will be mgh. I'll try that again. Potential energy will equal mgh. And that also means that if we let it go and our mass falls to the ground, then when it gets to the bottom, at impact, its kinetic energy will also equal mgh, because all the potential energy is turned into kinetic. Now, let's just break this down for a second. The kinetic energy at impact is going to equal mg times h. So it's going to equal the force that's acting on the mass multiplied by the distance. So it's going to be mg, which is the force, times the distance. Now that's important. If we now move over to the electric field world, we've got our positive charge. It's down here at the moment, which is probably where it wants to be. And if we lift it up this way, then we need to do work on this charge. In the same way that we had to do work on our mass, which is the force we have to do to lift it multiplied by the distance, so it's mg times h. Here, if we lift our charge, or lift in inverted commas, our charge from the negative plate up to the positive plate, the force we have to overcome is QE. And the distance we have to move it is not h, but it's d. And so the work we need to do to lift this charge from the bottom to the top will equal QE times d. Excuse me. So that's the work needed to lift it up to the top there. So the work done to lift it to the top will equal QED. Now if we let this go and accelerate towards the bottom plate, then at impact, the kinetic energy of our charge, our single positive charge, is going to equal the energy or the work that we had to do to get it up there in the first place, which is QED. QED. Now let's have a look at this again. Remember, gravitational fields act on mass. Electric fields act on charge. Here, in working out the kinetic energy, it was the mass multiplied by the strength of the gravitational field. Here, it's the charge multiplied by the strength of the electric field. Over here, we had to lift the mass up a distance of h, and over here, we had to lift lift the charge a distance d. So once again, there's a similarity here. Okay, so what's all this got to do with the electron volt? Well, now let me show you. Remember at the beginning, we said that the strength of the electric field is equal to the voltage between the plates divided by the distance. Well, let's run with that for a second. So, if the kinetic energy of our charged particle, as it's accelerated across the plates and hits the negative plate, the kinetic energy will equal Q, E, D. But we have already established that E equals V over D. So if I now take V over D and substitute it where I see the E, here, I will end up with the kinetic energy of our charged particle as it hits the opposite plate will equal Q times V over D times D. And the D's cancel. And so what we end up with is the kinetic energy is equal to Q times V. In other words, the kinetic energy of our charged particle will simply equal the charge on the charged particle multiplied by the voltage between the plates. Now, traditionally, charge is measured in coulombs. So if we want to work out our charged particle, the kinetic energy of this charged particle as it hit this bottom plate, it would be the charge on the electron, the charge on the proton, which, if it's in coulombs, it'll be 1.6 times 10 to the negative 19 coulombs multiplied by the voltage across the plates. Well, let's make the voltage here 5 volts. So the kinetic energy of our proton as it accelerated across this field will be the charge on the proton times 5. And that will equal 8 times 10 to the negative 19 joules. Okay, so that would be the kinetic energy of our charged particle as it hit this negative plate. It's simply the charge on the particle multiplied by the voltage. Well, it makes matters a lot easier if, rather than using the fundamental charge as 1.6 times 10 to the negative 19 coulombs, why don't we just call the fundamental charge on an electron or a proton simply one elementary charge? And that, in fact, is what we mean by the term elementary charge. E, which is the symbol for elementary charge, for one electron or one proton has the value of 1. 1e, one elementary charge. So the charge on one proton is 1e, the charge on one electron is negative 1e. As a matter of fact, it's the other way around because the elementary charge relates to the electron. So E is the charge on an electron, which is 1. So how can we use this idea to make this whole thing easier? Well, it's very easy, because now to work out the kinetic energy of our charge that accelerated across the plate, remember, it equals Q times V. But if we now use E, which is 1, rather than this value, then it's simply going to equal 1 times 5, which is 5. That's our kinetic energy. But hang on, it's not joules anymore. That's a different number to 8 times 10 to the negative 19. And so the new unit we're using here is the E electron volt. So 5 eV. So this charge, the two ways we could measure this charge, or the two ways we could quote the energy, I beg your pardon, on this charge is either 8 times 10 to the negative 19 joules or simply 5 electron volts. Now you'll notice that it was accelerated across a voltage of 5 volts. And that is why the electron volt is such a useful way of measuring the energy, particularly of charged particles, because the voltage that we are accelerating the charge across will directly give us the energy of the particle if it's a single charge. And so if this was if this was 10 volts across the plates, then a single proton that is accelerated across the plates would have 10 electron volts of kinetic energy at the other end. And now we can also hopefully see that if we now reverse our voltage, if we made the bottom plates positive and the top plates negative, we could actually push our positive charge the other way, or alternatively, we could stop it from getting to the other side by applying a stopping voltage equal to 5 volts. So not only is this a really convenient way of measuring the energy of a charged particle, but it also allows us to very, very easily calculate and measure that energy by simply reading off the voltage we need to use to stop the charge from getting across. And that is the electron volt, okay? And, pardon me, it is a very, very convenient way of measuring the energy of subatomic particles that can be accelerated across a voltage. So charged particles are often when we're dealing with charged particles, often we measure the energies in electron volts. A couple of final points. You will often see when dealing with charged particles accelerated to very high velocities, we might be talking about keV, which is kilo electron volts, or MeV, which is mega electron volts, or GeV, which is giga electron volts. And often if you do read any literature or any articles about the particle accelerators, either in Australia or in Europe, they'll often quote the power or the ability to accelerate electrons or charged particles using these sorts of values. Kilo is 1,000 electron volts, 1,000,000 electron volts, and 1,000,000,000 electron volts. So that's sort of quoting the sort of energies that you can accelerate particles at or up to in terms of energy. Okay, so that concludes our lesson on the electron volt. I hope it gives you a bit of an insight into where the electron volts come from and therefore how we can use it in the photoelectric effect. Thank you.